So Sahil Sri Mani Yenshwath Gandhi from NVIDIA Corporation. Now, a theme you'll see throughout today is the application of AI to verification, which is becoming even more popular. And I think probably every single booth you see along here will have some application of AI to verification on their stand. So it's a very important topic to make our verification more efficient. So the title of Sohail's talk is Overcoming the Challenges of Blending Hardware Verification Expertise with AI and Machine Learning. So he is a senior compiler verification engineer at NVIDIA Corporation with over 6 years of experience specialized in software development, test automation, and machine learning. His career includes roles at NVIDIA and Intel and has been focused on developing innovative automation frameworks that significantly reduce testing times and costs. Sahil holds 2 master's degrees, one in computer science and engineering from Pennsylvania State, and another in machine learning and artificial intelligence for LJMU. Is that correct? Yeah. Over to you. Thank you.
Hey everyone, good morning. So as introduced, I'm Sohail and I'm a senior software engineer working for NVIDIA Corporation. And today's topic, overcoming the challenges of blending hardware verification with AI and machine learning. So let's dive right into it. All right. So today we are going to discuss the verification challenge, the core problems we're all facing day to day. And we are going to move on with the AI promise and the pitfalls. So the realistic view at the new technologies that we are having today, practical frameworks. So when to use machine learning and when to use LLMs. So choosing the right approach. And we are going to discuss 2 case studies. The first one is predictive test selection in CI/CD pipelines. And the second one is intelligent log analysis for debug using LLMs. And finally, I'm going to wrap up with building a hybrid strategy and also talk about actionable best practices. Okay, so to get started, the verification challenge. So what exactly is happening? So as we know, AI is a buzzword in today's era. And the fundamental challenge in verification is that the complexity is growing exponentially, but our resources are not, especially for the smaller firms or startups. It's not so easy for them to upgrade their hardware with emerging technologies. And it's not even feasible to expect them to do so on exponential basis. So the common pain points we are all experiencing today in the world of verification. So let me walk through them one by one. The first one is endless regression cycles. So I think it's a common problem that's seen in the field of verification. So we as engineers, it's super problematic to run the full test suite in a slow and expensive environment, creating a bottleneck for each and every single code change or a review. It's not feasible. So that's the first point. The second one, debugging haystack. So failures in complex multi-component systems generate massive noisy logs, and finding a root cause can be a painful manual search. And finally, coverage versus reality. So although our test suites as part of our frameworks, even if we are hitting 100% code coverage, that doesn't mean that we have guaranteed we have certainly found all the bugs. So there is no guarantee that we have found all the bugs. The most critical bugs often hide in the corner cases that the test plans generally miss, or it's not 100% hit rate every time. So these kind of problems that I have highlighted requires us to move beyond the traditional brute force methods that we were using, and we need to work more intelligently. And let's see how AI can help us. All right. So now let's discuss what AI is promising and why is it promising, and the common mistakes or pitfalls to avoid. So AI definitely offers a path to work smarter, but it's always crucial, and it's necessary to beware of the common mistakes that our engineers face on a daily basis. So let's talk about what AI is ready to offer. So the promise. The first one is prediction. So when I say prediction, it could be forecasting high-risk changes and guide testing where bugs are most likely to be. It's kind of predicting what can go wrong. And once we have done that, the next part is optimization. So in optimization process, we are trying to intelligently select a smaller subtest of the tests or the test suite that can cause the highest impact. So this change from use case. It's totally dependent on each use case. For instance, there is a project where there are, let's say, 10 use cases the engineer is working on, and each use case might hit different code parts in the repository. For each change or a review, it might not be necessary to test all the code parts or the entire repository, which might take long time, and it is not even feasible in long run. So optimization is certainly necessary because AI might help us identify the smallest tests that could cause a significant impact for the change that was committed. And finally, the insight. So it is very crucial to automatically extract the signal from the noise and massive data or the log files that are getting generated. It's easy to probably analyze a log file that's few kilobytes long or probably few megabytes, but there are few use cases in heavy or complex loaded systems. Uh, the log files can even go beyond gigabytes or even reach uh, probably more than 10 gigabytes log, which is not really easy to analyze. So moving on to the pitfalls or the frequent mistakes in adopting AI. So the first one, magic wand thinking. So this is probably, I can say it is an expectation that is set by the industry, or expecting AI to be a drop-in replacement for engineering expertise, which probably many of us are thinking, or that's the common sentiment that's going on around the industry, that it is going to replace everything. But in my opinion, AI is a tool to augment and not replace our judgment. So end of the day, no AI can replace the human judgment, especially in the corner cases, or something that cannot be predicted very easily. So I would say AI is very good to act as an augmentation rather than a replacement. And second thing, wrong tool for the job. So right now we are aware of many models and many available use cases or many sources from which we can. Sorry? No, they're changing, they're updating. Yeah, I'm talking about the last point. So the wrong tool for the job. So using a complex LLM, a large language model, for a simple data classification task, or using a simple statistical model, it could be a simple linear regression model, when you need to understand some kind of unstructured text. So these kind of mistakes, if the engineers are not aware of the fundamental technologies or the right tools to use. So it is very necessary to pick the right tool based on the use case because they can vary. And finally, garbage in, garbage out. So the single biggest point of the failure can be attributed to this point because AI models, I think AI models find use with the when a clean and foundational data is available, and also when it is in a well-structured and relevant in a relevant format that can be used as a training data. So if your data is noisy, or if your data is not kind of relating to the use case or the solution that you're trying to look for, um, the result is gonna look like a noisy one too. So when you need the right result, you need to analyze the right data or pass in the right data for the training purposes. And so this slide kind of summarizes or helps engineers make a decision based on the use case. So I'm going to talk about two types of tools. So the first one, is machine learning, and the second one is the large language models, which are denoted as LLMs. So the core strength. So machine learning is known to solve a predictor and a classifier use cases, whereas LLMs can be acting as a good parser and generator tools. Machine learning models are good for structured or a numerical data or a code metrics or a performance stats. So it kind of involves a structure or a numerical format and a proper or a semi-structured representation of a data. But LLMs have been pretty effective when used for unstructured data segregation or trying to analyze the log, specs, code comments, or even bug reports. Whenever there is no structure, it could be a book, it could be a newspaper, it could be anything. And few use cases that are suggested for machine learning are predictive test selection, performance trend analysis, and bug triage classification. Whereas log parsing, summarizing, summarization, generating code coverage models, and also automating documentation, these are very good use cases for LLMs. All right. So case study one. Let's talk about the compiler analysis, compiler performance regression analysis with machine learning. So the problem statement in a large compiler project, let's say we are talking about some kind of LLVM, a code change might pass all the functional test cases, but it can introduce, let's say, a 2% subtle performance degradation on a critical or a crucial customer benchmark. So this is actually a big problem. Although it is functionally accurate, it is introducing a regression that the engineers need to catch and be aware of. So how do you detect it reliably? So the traditional approach or the legacy approach is static threshold. So the way that's generally followed is to run this benchmark multiple times, let's say 20 to 100 times repeatedly, and average the result and compare it with the average from previous commits. So that way we will understand if there is any change in performance. And also the performance engineers need to set a threshold when testing for such use cases, because there could be run-to-run variation, and there could be some noise that's accumulated as part of the run. So for instance, a regression, something can be flagged as a regression if there is a performance drop of, let's say, more than 10% or more than 8%. So setting the right threshold is important, because the regression, let's say 1 to 2%, could be a noise. It might not be a real regression at all. So the limitation, as I discussed, it could be extremely noisy. So normal run-to-run variations can easily exceed 3%. So it's very important to set the right threshold. And how can we solve this using the ML technique? So time series anomaly detection. The same issue can be solved using this using the smart way. So Instead of running this benchmarks repeatedly, treat the historical performance of each benchmark across hundreds of commits and treat that as a time series. So this kind of captures the natural patterns and variations and profiles noise over time. So this is a crucial aspect of model training. So train a forecasting model, let's say ARIMA model or a more advanced LSTM model, to learn this historical pattern. So the model's job isn't to know the exact performance, but to predict what could happen or what could be an expected performance and a confidence interval for the next commit. So here we are actually preserving the hardware resources and not extensively using by rerunning the entire test suite again and again. And finally, the inference. Whenever a new result comes in, it's checked in against the model's dynamic forecast. So if the result falls outside the predicted confidence band, it's flagged or it can be flagged as a statistically significant anomaly, which could probably be a regression. All right. So case study 2, intelligent log analysis with LLMs. So the problem, a complex simulation using open source HDL tool like a Verilator fails, produces about 100 MB log with interleaved messages from dozens of modules. So the traditional or a legacy approach. So engineers have been manually analyzing, probably using command line tools, the famous grep command or AWK, and custom Python scripts, writing a small script to handle the log file that's being generated based on the use case. So engineers rely on tribal knowledge and experience to search for specific error strings. And the limitation is that this is slow, brittle, and it's not easily adaptive for other use cases. So we can't easily correlate the events because, yes, yeah. So whenever we are looking for a specific event, it could differ from use case to use case, and the same scripts might not be used for multiple use cases. So now let's talk about the state-of-art LLM approach. So by default, LLMs kind of offer a semantic log analysis. So there is no pre-processing that's required. Instead, the smart way is to feed the entire raw unstructured log file directly into a powerful LLM. And you need to be making sure that you're prompting it right. So here is the concept of prompt engineering. So chain of thought prompting. So instead of a simple query, guide the LLM's reasoning. You tell LLM what to do. So how do you do it manually? Explain it to LLM so that it can kind of mimic what we are trying to do manually. So I would say first, identify all unique messages types and their formats in the log that's getting generated. And next, create a chronological timeline of all the transactional error messages that the user might be looking for. Then correlate those errors with any FIFO overflow or warnings that have occurred in the previous 1,000 block cycles. And finally, based on this correlation, we are trying to hypothesize the most likely root cause of the failure. So this moves from a simple keyword searching to an automated semantic understanding. LLM can comprehend the context and relationship between different events happening in the log file, and it could also provide the insights that are nearly impossible to find manually. All right. So now let's talk about the best practices. So start small and solve a real problem. Don't try to build a universal AI for configuration or AI for verification platform. Instead, pick one high pain, high value problem, like the most time consuming one in your day-to-day life whenever you're trying to debug something. So build a targeted solution aiming to solve it. And again, AI is here to augment and not replace. So the goal of AI is to be a co-pilot for the engineers. It automates tedious data gathering or the mundane task analysis, freeing up the experts to make a final critical decisions. And also build a solid data foundation. As I told, higher the value of data, higher output of the accuracy, higher the accuracy. So If your data is really good and clean and valuable, the results are going to be the same as well. And always keep the humans in loop, because end of the day, engineers are the real experts, and they will be the domain experts who will validate the tools, provide a feedback, and ultimately determine whether these technologies are going to succeed, and also bind them in a way that are favorable for the usage. And finally, to conclude, the verification crisis is a data problem, and AI provides a new set of tools to tackle it. And always be strategic. The goal is to augment, not to replace, and start now and start small. I can take any questions if you have any.
Are there any questions in the room? There's one over there. There's just one there. Yeah, can you just say your name and organization, please?
Yeah, I'm Jansi Gautam from Marvel. I had a question about the garbage in, garbage out when you spoke about regression data being structured. Yeah, the next slide.
Okay.
Is there anything that you treat as garbage in data? Because looks like you have put that in test results as a structured. Do you do anything with regression data that you come in, like, do you treat anything as garbage in?
Yes. So as I told, so this is a concept that we need to keep in mind whenever we are trying to develop a solution. So let's say you're trying to solve a problem. In our case, it's the regression. So the regression cycles can happen for any test case in the benchmark that we're trying to run. And these test cases could be targeting a single workload or multiple workloads. So there are some key variables that you can relate from the experience that we have been working on, that a specific test case or a specific benchmark or a test suite is based on few factors or the top contributing factors. So whenever you're developing a solution that's ML based or LLM based, so whenever you're trying to design a prompt or whenever you're trying to create a model, keep these factors in mind, because they're going to decide the result of your solution. So that is why I'm saying the data is the real I think the data is a real asset here. Like, there is a popular saying, data is the new oil. So the cleaner your data, the accurate your data, I think higher will be the accuracy of your result as well. So let's say you're feeding in the data that's not really important to determine whether there is a regression. The model might not be very accurate, and it might not meet your standards that you're looking for. So that is what I meant by garbage in, garbage out. So it totally depends on your data that you are trying to solve.
Okay.
Yeah.
Okay, thank you.
Thank you.